presented by Caltech.
Welcome, everybody. So the news that everybody has known for a while now is now official. Announced at 7 o'clock this morning was the fact that on August 17th, LIGO detected the signal from the merger of two neutron stars, followed about 2 seconds later by a gamma ray burst. And since that time, astronomers all over the world have been rushing around, following up this event at every conceivable wavelength. And it's been quite an exciting time. And what we want to do is share the news with a local angle, the people here at Caltech who have been very involved in this effort. We're going to have four faculty speak, starting with Alan Weinstein, professor of physics, who leads our local LIGO data analysis effort. Mansi Kasawal, the PI of the Growth Network, which is a team of astronomers worldwide who follow up transient events. Greg Hallinan, professor of astronomy, who is a discoverer of the radio counterpart of this event. And finally, Rana Adhikari, who works hard trying to beat the noise down in the LIGO detectors and is thinking about the next generation already. So without further ado, I'd like to ask Alan to come up and start the presentations. And I'll say that after you're welcome to go out, after this is over, you're welcome to go out to the Cahill patio for coffee and snacks.
A little bit of the local angle here. You know that here at Caltech, we are the LIGO laboratory, us and MIT, and we've been involved in, well, searching for this kind of event for decades. And I'll tell you a little bit about it, but I'll first start with August 17th at 6 in the morning here, kind of a little bit early for me. I was very groggy. I was greeted with this data. At the very top, actually, is the LIGO Hanford data. Here's LIGO Hanford Observatory and LIGO Livingston Observatory. Remember, these detectors were sort of invented, designed, built, operated, upgraded continuously for 20 years by Caltech and MIT, and we're very proud of them. As is often said, they're the most sensitive measuring devices on Earth, at least that's the way we like to think of it. And the data that usually comes out of them is noise. In fact, here's the Virgo, data from the Virgo detector. You don't really see anything there at all. Here's the data from the Livingston detector after we did a little bit of cleaning up of it. When we first looked at it, it really didn't look anything like that at all. But at the very beginning of that morning, I was very groggy. I was sitting at my computer because I was woken up by a text message, a loud text message. And I saw this thing, and I went, wow, this is pretty amazing. We have seen in the last 2 years a bunch of binary black hole mergers that show up in data like this, sort of like that little last bit over here, sort of the last second or two. These are time frequency spectrograms. This is the moment at which the two neutron stars merge together, and there's 30 seconds before that. Actually, thank you. And actually, the waveform continues in the minus direction in time, well, for millions and millions of years, but it begins to enter the LIGO band at about 20 hertz, about 100 seconds before. And about 100 seconds before, you can't really see much here, it's mostly in the noise. What we usually detect when we detect binary black holes is just a little bit at the very, very end there, and that gets us very excited. After the fifth or sixth, we're not so excited. But this was different, very different, much, much longer, So we knew it wasn't a heavy binary black hole system. It was a much, much lighter system. I'll try to explain how we knew that from this. But already I was extremely excited. Got on the telecon with some of my colleagues. There were people there from the East Coast and from Europe. So they had been up for a while already. I could tell from the telecon, straight through the telecon, the unbelievable excitement of the handful of people that were there. They were just shaking in their seats. I didn't only hear it in the telecon, I could almost feel the gravitational waves that they were emitting. It was so violent, actually. So I knew that something was going on at that point. The fact that these are much longer tells us something truly new and different was being observed. It has been, we anticipated this, of course, for many, many, many years. Even the LIGO detectors were built for detecting these kinds of very long events. But we trained ourselves to expect that the first time we would detect it, it would look sort of like the stuff at the bottom that Virgo saw. In other words, pretty much all noise. And the reason is that we're likely to detect these events very, very far away because there's more space much further away than there is close by. And we never expected them to be close enough to see the trace in these kinds of displays. We would have to rely on the computers to figure that out. I had no expectation that the first binary neutron star merger that we would detect would be so loud that we would see it in traces like this. This really was astonishing to me. It was like more than a dream come true in some sense. And not only that, there was this at the same time. Okay, here is the combined information from the LIGO detectors about 8 seconds before merger. There's that line over there. Here's -8 seconds plus 6 seconds. And these traces here come from space telescopes, gamma ray telescopes. And in particular, if you look at the middle one here, this is the Fermi space-based telescope, the gamma ray burst monitor. And there is a thing about 1.7 seconds later. Now that was pretty astonishing to me as well. And the reason for that is that gamma ray bursts are very, very beamed. We knew that binary neutron stars can produce beamed bursts of gamma rays, but the chance that they'd be pointing straight at us was very, very low. I did not expect to see a gamma ray burst the first time I see a gravitational wave from a binary neutron star merger. That was a big surprise. But what was even a bigger surprise is that all gamma ray bursts that have ever been measured before were very far away, something like, billions of light years away. But we already knew from here that this merger happened not billions of light years away, only 100 million light years away, close by. If a gamma ray burst happens 100 million light years away, it should be astonishingly bright. This peak should have been through the roof by 2 or 3 orders of magnitude, and it wasn't. It was, in fact, an extremely wimpy gamma ray burst. And I had no idea why, and I hope that my colleagues will tell you why. Hope so. We did immediately detect this event by matching it with our predicted waveforms. We had a bank of many, many different predicted waveforms that were prepared for us by many of our colleagues, especially the SSX Simulating Extreme Spacetimes group here at Caltech and Cornell, now spread all around the world, but these guys are the world's experts at these things. These events here were the 4 of the events that we observed a little bit earlier. I don't know if we can do something about the light so we can see it a little bit better in the room, but anyway, whether or not. The point is that these events, you can see, are pretty short, less than 1 second long. And there's a reason for that. They last a short time in band because they're very massive stars, and very massive stars are big. I mean, black holes are big. Not as big as regular stars, but they're very compact. But the more mass a star has, the bigger it is, which means that it smashes together. And these little bits at the end are the smashing together part over there. So maybe we can see a little better now. These little bits at the end are the smashing together part. And that happens when the black holes start touching each other. And they touch each other earlier when the stars are bigger. Okay? Black holes might have radii of, these ones in particular might have radii of 100 kilometers, a few hundred kilometers. Okay, so these are two stars orbiting each other a few hundred kilometers apart, moving at close to the speed of light, 2/3 of the speed of light by the time they smash together. The event that we observed, let's see if I can get this to work. Oh boy. The event that we observed, if I can get this to work. There it is. You can hear it. It's a little bit of a rumble. Low frequencies. When it enters the LIGO band, it's at low frequencies. But this object is so much smaller that it orbits for a much, much longer time in the LIGO band, from 25 hertz or so up, until it finally can smash together. And when it smashes together, amazing things happen. But it takes a lot longer for it to happen. It's still at pretty low frequencies now. You can barely hear it. I don't know if you can hear it. Hear anything? We're still about 30 seconds away, about 20 seconds away. You see all these shorter guys, they're gone by after a fraction of a second or so. But this one lasts in band for a very, very long time. These are precisely calculated waveforms. And so here it's starting to happen. I start hear it. I don't know about you guys. You know, for 20 years, I've been giving talks about how one day we're going to discover gravitational waves, and it's going to sound like that. Whoop. But these guys, they're like, I'm serious. You have to turn up the frequency to have them sound like anything at all. This one, we didn't turn up the frequency. Now, this is a simulation, but if you listen to the data, there's noise behind it. Sounds just like it. Okay? For 20 years, I've been waiting for that sound to come from nature. We know that these kinds of waveforms are well described, what we actually detected in the data. Here's the LIGO data once again. It's probably the third time I've showed it already. This is about 30 seconds before. And here's where we subtract one of those waveforms, the one that best matches the data. And it's just noise, nothing else. And this is 3,000 cycles in band. And it matches so well that when you subtract it, you see nothing over the last 30 seconds or so. That tells us that two things. First of all, we understand what this signal is telling us pretty well. And that means these templates are based on solutions to Einstein's general theory of relativity. So it tells us that this signal is very well matched to the prediction for general relativity. That means that we can trust these signals well enough to extract information such as the masses of the particles, the masses of the objects. And here, for example, is a graphic of the masses of the objects that LIGO has already detected in gravitational waves. These blue guys over here are LIGO detections. They're binary black holes. On the y-axis is the mass of these objects. The mass of the sun is 1, and then this ranges from about 5 to 80. And these are very massive objects. The purplish ones are black holes that are observed in our galaxy from the X-rays that fall into them. And there's quite a bunch of those, and they tend to be somewhat lower in mass. Neutron stars, isolated neutron stars, can be observed as pulsars, and there are many experts in the audience who know a lot about pulsars, and there's a lot of them in our galaxy. These are all strewn about in our galaxy. The x-axis, by the way, doesn't mean anything at all. It's just for prettiness, to spread them out. And those neutron stars are all measured to be somewhere between maybe a little bit less than 1 solar mass to about 2 solar masses. And so these stars, they're both, by the way, dead stars. Both kinds are dead stars, right? Very massive stars, maybe more than 30 or 40 solar masses, will burn all the nuclear material in their core until they're burned out. That will cause the core to collapse. The outer layers will be blown out in a supernova, spewing the interstellar medium with pollution, carbon, oxygen, nitrogen, that kind of stuff. That stuff recoalesces into second-generation stars like ours, and planets, and people. You know, we are stardust. But it leaves behind a dead remnant. Either, if it's a very massive, if the original star, the progenitor star, is very massive, more than about 20 or 30 solar masses, a black hole, which could be as much as 5 or more solar masses, or if the original star was less, between 10 and 25 solar masses, something like that, it'll collapse into a neutron star, which will be somewhere between 1 and 2 solar masses. So these are both sort of dead star kind of things. These are the stellar mass black holes, and these are the neutron stars. You might wonder whether there's a gap in between. We're not quite sure. We don't really know whether there's a gap in between. And what we really don't know, and here are the masses of the two objects that we observed just in August 17th. Here's their final object, and it's got a little tiny question mark here, okay? And that's because we don't really know what's left behind. Is it a neutron star? Is it a black hole? Whatever it is, in fact, it could be something in between. There could be a hypermassive neutron star that's produced that might last for either a fraction of a second or maybe many, many seconds, vibrating like crazy and producing a lot of gravitational waves at high frequencies. And the thing is that at high frequencies, the noise, and I'm talking about a kilohertz, 2 kilohertz, and up, okay? At these very high frequencies, the noise in the LIGO detectors gets worse. So much worse that we don't really detect the signal from that final object, even though this source was so close. It was only 130 million light years away. Even though it was so close, still that final high-frequency stuff is buried in the noise. We got to do better. My colleague Rana Adhikari will tell us how we will do much, much better. So we really want to know what's left behind. One thing that we do know is that although these dead stars polluted the interstellar medium with us, okay, when they finally merged together into a single object, that single object, well, in the process, an enormous amount of material is ejected. Maybe so much that what's left behind is a neutron star, maybe not enough so that what's left behind is a black hole. Maybe some of it falls back in so-called accretion disks. We'd like to know much more about that. And so we are learning much more about that from the electromagnetic radiation that my colleagues Mansi and Greg will tell us about. Also, when these things come together, they really can pull on each other very hard. When they're, I mean, this is a sort of, here are the two stars very close, on the order of 50 kilometers apart. Here they are tearing each other apart. This is called tidal distortion, when they start to tear each other apart, and disruption, when they totally rip each other apart and spew a lot of material out into the interstellar medium. And what's left behind, we're not sure, but what we do know is that when this tidal distortion starts happening, it tells us about the size and the amount of material stretching that this nuclear material can produce. And that tells us about the properties of the nuclear matter that these neutron stars are made up of. So we're doing nuclear physics. And what we've determined is that we can't really tell, because it's in the noise really, we can't really tell just how small these objects are, but we know that they've got to be smaller than about 14 kilometers. We didn't know that before. 14 kilometers, that's about, well, compared to LA, it's pretty big, but that's the mass of the sun over there. For the physicists, we've learned a tremendous amount. The gravitational wave signal is fully consistent with general relativity, beautifully so, and will be over several thousand cycles, and we'll have papers on the subject very, very soon. We learned, and in fact, for 2 decades, I've been talking about what we will learn from gravitational waves. As a physicist, we'll learn about the fundamental properties of gravitational waves. They move at the same speed as the speed of light, and they're polarized in this very particular way called tensorial polarization. We want to prove it. We can't just accept it. Those are predictions from general relativity. You need to test those predictions. We have found that the polarization is consistent with tensorial, not vector or scalar, to very, very high accuracy. We found that, by measuring the cycling of the gravitational wave and comparing it to what it would be like if there was some distortion due to dispersion, different frequencies traveling at different velocities, we know that the dispersion, which allows us to measure the graviton mass, is consistent with a graviton mass of 0. We also note that these gravitational waves and the gamma rays from the gamma ray burst have been traveling for 130 million years, 10 to the 16 seconds, and they arrived within 2 seconds of each other. That tells us that gravitational waves travel at the speed of light to 1 part in 10 to the 15, even though gravitational waves have nothing to do with light whatsoever. It's the speed, the fastest speed sustainable by space-time. Firm prediction of general relativity turns out to be right. We did not know this, by the way, on August 16th. We knew it on August 17th. And both the gravitons and the photons fell into the gravitational potential well of the Milky Way galaxy over the same time. Okay? Galileo checked that out with a rock and a wooden ball. They both fell at the same time in Earth's gravity. Nature allowed us to observe nature doing this with gravitons and photons. They fell at the same rate. Principle of equivalence, once again. For the astronomers in the audience, we need to know within minutes where the source is and tell them where to look. Here is the arc of LIGO, the 2 LIGO detectors locating the source in the sky, somewhere along this arc, from timing alone. And then from amplitude information, the LIGO detectors knew it was somewhere in this blue region or in this blue region. But now we have the Virgo detector. But the Virgo detector didn't see anything. That probably means that it was in sort of a blind spot of the Virgo detector. Somewhere closer. All, by the way, gravitational wave detectors have blind spots. LIGO has blind spots like this as well. They're in a different place in the sky. This event happened to be in the Virgo blind spot. Virgo didn't detect it, which means we knew that instead of it being somewhere in this blue region, it was in this much better localized region, only 30 square degrees that we could tell our colleagues where to point. At that point, I knew I had to do something really, really fast. So I went to the bathroom. And when I came back to the bathroom, I immediately contacted Nancy and Greg and Fiona and told them, asked them, is there anything in that spot? Point your telescopes, do it now. This is the real thing. This is not a drill. And they all paid attention to me for the first time ever. And I wondered whether this was the dawn of gravitational wave multi-messenger astronomy. And I hope that Nancy will tell me something good about that.
So, does this one work? Yeah. Okay. All right. So thank you, Alan. Good morning, everyone. I'm going to tell you a little bit about now the light. So Alan woke me up at 6:58 a.m. That morning, and I couldn't believe the text message on my phone. It said 2 neutron stars, a burst of gamma rays. This was unbelievable. So first things first, my 2-year-old had to learn a new word. It was called neutron star. And then he had to be promptly handed off to daddy because mommy had to swing into action. So Alan told us that with the gravitational waves and the gamma rays combined, the localization was 30 square degrees. This was the smallest ever, but 30 square degrees is about 5 full moons by 6 full moons. That's a pretty big area on the sky. So finding home is not that simple. So what we wanted to do was, so what we had to do was, I called up postdoc Dave Cook, who looked inside this 30 square degrees and found 49 galaxies in the error circle using the Census of the Local Universe Galaxy Catalog. Now, which of these 49 galaxies was really home to this neutron star merger? So we sorted this galaxy by stellar mass. The more massive the galaxy, the more likely it was to be the home of the merger. And we set off to point every telescope we could get our hands on to hunt for which galaxy was really it. So our panchromatic hunt was as follows. The first satellite that flew to this list of galaxies and started marching down this galaxy list was the SWIFT satellite, thanks to its principal investigator, Dr. Brad Senko, former student of Fiona's, who got onto the X-ray and ultraviolet search right away, within minutes of getting that phone call. So Brad and I talk to each other every time LIGO Virgo send us a trigger, and usually it's a very calm conversation because black holes are black, and we know we are doing the drill, and it's all okay. But this time when we spoke to each other, the sheer excitement in our voices was palpable. I mean, it almost seemed real at that point, and it was hard to breathe. Then at around 9 a.m., the next satellite, NewStar, Fiona had her entire team in a conference room just up on the second floor. And I met with them, and they started marching down the galaxy list in the hard X-rays, doing very deep integrations to look for hard X-ray photons. Next came the optical, but here we were in a fix. It was morning. That's a problem when you're searching for the optical. And the coordinates were down in the southern hemisphere. So I called my friends at Carnegie Observatories, and they assured me that with the 4 telescopes at Las Campanas Observatory, they had the optical part of the spectrum covered, and they were going to march down a galaxy list too. So we focused our efforts in the infrared with the Gemini South telescope and started looking for an infrared counterpart. Greg Hallinan here has a fantastic program on the Very Large Array, and he started marching down a galaxy list in the radio to look for the electromagnetic counterpart. But by far, much to everybody's surprise and joy, the most majestic aspect of this event was there was light at every single wavelength. So after about 10 and a half hours after the merger, when the sun set in Chile, my Carnegie friends were the first to announce the optical position of the transient. And minutes after that, there was light in the infrared bands, the ultraviolet bands, with the Swift satellite, the Gemini South telescope, about 8 other telescopes in Chile, and then there began a worldwide campaign. Now, radio, you had to be more patient, but wait for Greg's talk before you can hear more about that. So a global effort began, which spanned 70 telescopes all over the world in all 7 continents. 7 telescopes are actually in space, so in an 8th continent, if you want to call it that. But as the sun set, different telescopes lit up and started collecting data at the position of this transient, which was now localized to a galaxy, NGC 4993, that was only 40 megaparsec away. So only 120 million light years or so away, which is very, very close to home. So you can see this movie run through. I mean, this effort continued for a month, so this movie is very long. You can see the red is optical and infrared telescopes, and green are radio telescopes that are on the ground. And the radio telescopes are not really bothered by the sun here. They can observe any time, except when the sun flares. And Greg can tell you more about that too. So one advantage of being part of a global effort is that there's all this data coming in. We were personally, the growth team was looking at data from about 18 telescopes spread over 6 continents, and sleep is sort of very, very low down on the priority list. But with friends all over the world in different time zones, the team never sleeps. And the real powerhouse of this team are the students and postdocs sitting in the front row here. And you should talk to all of them because each of them took ownership of one of the instruments and telescopes. And as soon as the data came in, they analyzed it, added the data point, and were waiting and preparing for the next data point to roll in there. In fact, the youngest student, which is first-year student Kishale, hiding over there, had to write a telescope proposal in 2 hours for GMRT. I didn't think he could actually do it, but he pulled through. And we got that data too. So for those of you who like light curves, this is how the light evolved. So in blue, you can see the blue flash. It faded in just a few days in the ultraviolet and the optical wave bands. And in the red, you can see the long-lived red shine. It lasted for a few weeks, almost a month, in the very red JHK bands. So you had a blue flash and a long-lived red glow that was shining. So pictorially, here's an image from the Gemini South telescope. You could see that blue dot initially next to the galaxy, and very quickly it turned red. And the red light is key to the mystery that we were after, which is the nuclear physics. So let me give you some background before I tell you why that red light was just the most amazing and most brilliant discovery. And that is, let's look at the periodic table. So we know in the periodic table that hydrogen and helium were synthesized in the Big Bang. Then the cores of stars fuse them into slightly heavier elements. And then when stars explode as supernovae, you get all the elements marked in blue there, right? Type 1, type 2 decides whether it's light blue or dark blue. But the embarrassing fact was that on August 16th, 2017, we didn't know where half the elements in the periodic table heavier than iron were synthesized. Now, theoretically, they were supposed to be made in R process nucleosynthesis. The R in the R process stands for rapid capture free neutrons. So theoretically, again, for decades, it had been predicted that neutron stars smashing into each other, there's an abundant supply of free neutrons, and in this very violent explosion, things should happen. Some of these elements should get synthesized. But observers, well, we don't see it. We don't believe it till we see it. So we were patiently waiting for this day. And the thumbprint here, when we're looking for nuclear physics or for astrochemistry, is actually spectroscopy. So when Jacob Jenkson here reduced this Gemini spectrum, which is shown in black here, it was shocking. I've seen many a spectra in my career as a time domain astronomer, but never anything like this. So the things I'm excited about in this bunch of squiggly lines here are the two big bumps in J band and H band. So you see these two big bumps, because these two bumps are exactly what Dan Kaysen and Jennifer Barnes had predicted for heavy element radioactive decay 4 years ago. And that model is shown by the red line, okay? So we're not fitting to this data. We're simply overplotting a model prediction from 4 years ago, and they're spot on. And they base their predictions just based on one element, which, and you can see in the bottom to last row there, number 60, neodymium. It's an element used in infrared lasers and is known to have emission lines in the infrared. These big bumps here are a complicated blend of many elements. Anything marked in yellow is fair game here. But this one element is sufficiently representative that it could reproduce those two bumps. So this was already telling you that there's no question, there's almost unequivocal evidence here that there is heavy element production and heavy elements being synthesized. And there are beautiful spectroscopic sequences, like this one in particular was taken by Elena Pian using the VLT X-shooter instrument, where every single night there's data between 0.5 micron to 2.5 micron. And now you can model these thumbprints extensively in the weeks, months, years to come to try and figure out how much of which element was in fact synthesized. So I think we are all sufficiently convinced that this is definitely a site of heavy element nucleosynthesis. There's definitely elements in the periodic table that are synthesized here, but are they the site, right? Is this accounting for the gold and platinum and uranium and neodymium and other elements you can't even pronounce in the periodic table in that mass range? How much of that are these sites, in fact, how prolific are these sites? How much of it can they explain? So if you look at the observed solar abundance, then if these are the true cosmic mines, there are two numbers that matter. One is the amount of material synthesized by one such merger, which we can measure. And even if you do things very, very simply, back of the envelope, you can show it's more than 0.03 solar masses or about more than 10,000 Earth masses. Okay, so the first number we have a good idea of, as long as this one element represents them all, one merger represents them all. Now, the second number is the rate of mergers. So Alan told you how you could take one event and try to extrapolate the rate. So even if you take, again, a rough number, not the highest end, not the lowest end, a middling number, the rate would be something like 1 per 10,000 years per galaxy. And the product of those two is actually good enough to explain the observed solar abundances. So, of course, you need a full sample of neutron star mergers and neutron star black hole mergers to say this for sure, but there's already tantalizing evidence that this could not just be a site, but the site of heavy element production. And most importantly, what this 10,000 Earth masses means to me is that the future is literally bright. And bright as in photon-laden. Every time LIGO will go find neutron star mergers and neutron star black hole mergers, we should see a booming, bright optical and infrared counterpart. And next time it should be in the right hemisphere, I hope. And then right here in Palomar Observatory, which is just 130 miles from here, we are building two cameras. One is actually getting commissioned right now as we speak, which is this Wiki transient facility. It will be a 47 square degree camera. And in just a couple of months, we are putting together the Palomar Gattini IR system, which is a 25 square degree infrared camera, so that we can have both the optical and the infrared covered. And no matter what the size of that error circle, we should be able to find that blue flash and that red shine. So now I want to take a moment and step back and present you a concordant picture that unifies all the wavelengths. We have NASA to thank for the music. All right, point is you saw a simple so the point is that you saw a very simple picture where you saw two neutron stars merge, launch a jet, and then this kilonova radioactive decay of debris that went from blue to red, and then a forward shock interacting to give you radio and X-ray emission. This picture smells right, okay, but it doesn't quite look right. If you look closely, then the details are actually amiss. There are three big problems with the simple picture there. Problem number one, the gamma rays that were seen by the Fermi satellite are too wimpy. They are 4 orders of magnitude less luminous than any other short-hot gamma ray burst ever seen. So that's not good news. The second one is that the optical emission and the ultraviolet emission is much too bright, much brighter than any theorist had predicted based on heavy element radioactive decay. And the third problem is the radio and the X-rays and their late onset and evolution. So we had to come up with a new model to try and explain, fit the different clues here. And the model that we came up with, working with Udi Nakar at Tel Aviv University, is what we call the cocoon model. So what we posit is that when the two neutron stars merge, they launch a jet, but the jet is launching into a lot of stuff. It's not launching into clean material. So the material around the jet, actually engulfing the jet, forms a pressurized cocoon that expands out. And that's what you see here. And this pressurized cocoon could completely choke the jet. Right? The jet may never make it out, or it may in a different direction. But this pressurized cocoon, when it breaks out, gives you very wimpy gamma rays. The same pressurized cocoon accelerates the material so much that by Doppler effects alone, you can explain bright blue, ultraviolet, and optical emission, just like what we saw. But if this cocoon model is right, then what we have to do is wait for the radio, because if this cocoon model is right, there has to be radio emission. And radio emission with very peculiar characteristics that can break the tie between a cocoon that choked the jet, which is on the left side, and a cocoon that let the jet escape in another direction. So with that, I'd like to hand off to Greg Hallinan, who can tell you about how radio is going to solve the mystery here.
Okay, thank you, Mansi. Yes, I'm primarily going to talk about the discovery of the radio afterglow of this neutron star merger. But first, I'd like to talk about the morning of the event and touch on something that Alan already mentioned. He talked about the verification of this event at LIGO and the email that goes out to the astronomical community. So I was one of the astronomers lucky enough to get that email. However, I had made a very grievous miscalculation. The second observing one of LIGO had been ongoing for about 9 months. There was about a week left. And I thought, there's been no detection of any neutron star merger in the first 9 months. What are the odds it's going to show up in the next week? So my wife and I took our baby daughter to Ireland to meet our extended family for the first time. And when I got the email, I was standing in the grocery store in the northwest of Ireland, holding a very jet-lagged baby. And I saw this email come through, and my first reaction was, oh, wow! And my second reaction was, oh, no. I'm not at Caltech. What followed very soon after, in the same grocery store, was a frantic Skype call with Mansi, and also Kunal Mooley, who's one of the main people who was involved in the radio effort. And very quickly it became apparent that this vacation was finished. And the lesson learned is never underestimate LIGO to produce a spectacular discovery at a moment's notice. So, what kind of radio emission can you see from a neutron star merger? Well, Mansi's already described that you have a certain fraction of material ejected during the merger of the event. And that's where we think most of the heavy element nucleosynthesis might be happening. That same material is traveling outward at a velocity of about 20% the speed of light and slams into the gas and dust that surrounds the site of the merger, the interstellar medium, and forms a shock wave. At the side of that shock wave, you get radio emission. The luminosity and timescale of that radio emission strongly depends on the energetics of the explosion as well as the density of the environment. And it takes typically months to years for this radio emission to appear. Another possible source of radio emission is the presence of a relativistic jet. It has been long theorized that neutron star mergers may be the engine that are powering a classic explosion called short gamma ray bursts. These are bright bursts of gamma rays from halfway across the universe, seen on an almost daily basis. They must be powered by relativistic jets, and it's been long theorized that these GRBs are powered by neutron star mergers, which means, if that's the case, there must be a relativistic jet produced by this particular merger. One way to investigate that is look for radio emission. In this case, radio emission rises on timescales of days to weeks, rather than months to years. Once again, it's very sensitive to the density of the environment of the explosion, but now also very sensitive to our viewing angle of the event and of the jet. If you're looking down the barrel of the gun, down the jet, you'll see a much brighter, faster afterglow. If you're viewing off axis, it's slower and it's fainter. The third possibility, as already described by Mansi, is that maybe there's a delay between the launching of the ejecta and the subsequent launching of the jet. And the much faster traveling jet slams into the dynamical ejecta, forming this cocoon that Mansi has described. This also has a very characteristic radio signature. Mansi described the case where you have all the energy of the jet dumped to the cocoon. That will give you a strong radio afterglow. Or maybe the jet can break through, can punch through the ejecta and escape. That will give you a weaker radio afterglow. This now is on time scales of weeks to months. So we have months to years, days to weeks, and we have weeks to months. So what does that mean for our strategy with radio telescopes? Do we have to observe with every telescope every day for a year? Well, happily, the observations in radio don't happen in a vacuum. We are now in the era of multi-messenger astronomy, and we're able to draw on all the information present from gamma rays to radio. As already mentioned, we knew there was a burst of gamma rays 1.7 seconds after the merger. As Mansi described, we know within the first day there was an optical afterglow, an ultraviolet afterglow, and an infrared afterglow. What's very important for the radio was that an X-ray afterglow showed up after 9 days. Previous to this, both NuSTAR, managed here at Caltech, and SWIFT had been observing very frequently. And that had demonstrated that this afterglow wasn't some fading X-ray afterglow associated with the gamma rays. This is a new source of X-rays. And we also knew that much later again, an infrared source showed up, as found by Mansi recently. What was most important for the radio was the fact that you had this X-ray afterglow. As described in Mansi's talk, the model that we think can explain that is the presence of a cocoon. And if that's the case, the radio emission should show up very soon afterwards. And I had been talking very frequently to Mansi and Udi Nakar, and we were really gearing up when we saw this X-ray emission to do a lot of follow-up. And we observed with our telescopes almost daily after this detection. So here now is our suite of radio telescopes that we use for our follow-up. We were very lucky to have the Very Large Array in New Mexico, which remains the largest and most sensitive radio telescope on the planet. We had the Giant Meter Wave Radio Telescope in India lined up, and we had the Compact Array in Australia also observing on a daily basis. About a week after the X-ray afterglow, we finally saw our radio afterglow. On the left, I'm showing a radio image at the location of this galaxy. On the right, I'm showing one of Mansi's images where you see from Gemini. What you see, first of all, is a bright radio source coincident with the center of the galaxy. It turns out there is an actively accreting supermassive black hole at the center of that galaxy, and that's where this radio emission is coming from. So ignore that bright source and instead focus on this little smudge to the northeast. That is our radio source, which when I saw it first after 48 hours without sleep, I was a bit hesitant about, but Kunal Mully and I pored over it for about 6 hours, and we finally convinced ourselves that it was real. And happily, a few hours later, we heard from another colleague in our collaboration, Alessandro Corsi, who has separately been observing with the VLA at a different frequency and also detected the source. 2 days later, it was also seen by the Compact Array in Australia, and we knew we had our transient. But what really became the final evidence to show that it was real was that over the following 2 weeks, it increased by a factor of 2 in brightness. So we knew we actually had our transient. So what did we learn? Let's first get to the question of gamma ray bursts. Do we see or have we seen a gamma ray burst from this source? So there was, as has been mentioned already, a weak detection of gamma rays. but it was 10,000 times weaker than you typically see for a gamma ray burst. That's evidence alone that we're not looking down the barrel of the gun, like we are for the cases of normal gamma ray bursts. And indeed, follow-up with Swift and NuSTAR ruled out an X-ray afterglow that you typically see, and also there's other evidence that suggests such a weak afterglow won't be able to punch through and give you a gamma ray burst. So let's rule out the case that we're looking exactly on axis. But one theory put forward is that maybe we're actually observing this gamma ray burst slightly off axis, just catching the edge of the jet. Well, from the radio observations, that's where radio plays a key role. It turns out if that was the case, we'd have seen a very bright radio afterglow. We just don't see that. And that means we have to be observing this event from a very large angle, we're widely off axis. And that means we're not looking at a normal gamma ray burst. We're looking at a burst of gamma rays, which is different. And you need other models to explain that, like the cocoon model. What else do we learn? Well, first of all, we can very easily rule out the case on the left that the radio emission is produced by the same ejecta that gives you the optical and infrared afterglow, where we think heavy element formation happens. We do expect to see radio emission from this ejecta, but on timescales we think of a few months to a year. That leaves us with two possibilities. Is there a relativistic jet? Is there a cocoon? And it's very important to answer this question, because if it's a jet that actually escapes without interacting with material, then someone somewhere in the universe may see a gamma ray burst. It might not be pointing towards Earth, but somewhere else will detect a gamma ray burst. Or maybe you need a modified model, like the cocoon, that can explain all the photons seen from gamma rays to radio. So how are we going to actually answer this question? Happily, the radio story is still unfolding. We got our first detection long after most observers had stopped observing. They were all writing their papers, we were frantically reducing our data. The good news is that we're going to get detections, we think, for the coming months and maybe even years. And that will answer this question, I think, definitively. Here I'm showing our radio detections to date, and overlaid on this plot I'm showing the orange is the off-axis jet, and the two purple lines are showing our two cocoon models. So what you can see here is that very quickly, over the next coming weeks and months, we should be able to distinguish which of these models is actually at play. And we also have another very powerful way to try and investigate this question. It turns out these explosions are traveling, these types of ejecta travel at different velocities. So the fireball expands at a different rate and a different size. Here now I show the relative size of these three types of ejecta if the explosion was observed today. Here we show, for example, on the left, the dynamical ejecta. Here we have the relativistic jet, and here we have the cocoon model. On the left, it's supposed to show a little dot to represent the solar system, but it's so small apparently you can't even see it. So what we see is that our relativistic jet is actually much larger in size than either our dynamical ejecta or a cocoon. It's actually a few trillion kilometers in size by now. If we're able to directly measure that size, we have another way to directly distinguish between these two models, these three models. And it turns out at radio wavelengths, there is a way to try and do this. This source size is only about a milli-arcsecond in size. Very, very small, but by combining dishes across the globe, you can build a radio telescope that has the resolution and sensitivity to actually detect this. This is an array called the Very Long Baseline Array. It involves 10 dishes spread across the US and beyond, including one dish at the Owens Valley Radio Observatory managed by Caltech. To this array, to make it even more sensitive, we have added in the 27 dishes of the Very Large Array and the giant dish at Greenbank. These 38 dishes combined are now being used to try and directly image the explosion, the debris of this explosion, allowing us to measure the size for the first time and determine the velocity of the ejecta. And we hope that this will finally resolve the question of what type of ejecta we are seeing, whether or not a gamma ray burst was seen somewhere in the universe, and other fundamental questions. So, what is the path forward? We have learned so much, but this is the first detection. This is just the beginning. we have so many questions to answer. What is the true neutron star merger rate? We've got a sample of one. We need a sample of many. Mansi talked about the heavy element formation. What fraction of heavy elements, very precisely, are produced in this channel? Have we found the engine for short GRBs? We've got strong evidence there's a relativistic jet, but is there a GRB seen somewhere in the universe? And finally, can we infer the nature of the remnant? Is there a hypermassive neutron star, or is there a black hole formed? These are all very important questions that can be answered going forward in the era of gravitational wave multi-messenger astronomy. Some of these questions can be answered by advanced LIGO in the next couple of years, and some will take a lot longer. And to give us a perspective on that future, I'm going to hand over to Ron.
So there are a lot of questions about the future, but I thought we should look a little bit at the past to see how did we get here. I think this is a story of a combination of experimental and theoretical physics, which have really started here in the early 70s and has been going on at this rate, extreme rate for so long. This is Vladimir Brzezinski, who passed away soon after the detection. He's really one of the really forefathers of precision measurement and taught us how to think about the real quantum limits of detection. He used to visit here every spring and would sort of wag his finger at us if we were doing anything a little bit not at the ultimate limits of the laws of physics. Down here is Carl Caves, who was a grad student here in the 70s. He introduced the idea of basically, you're not really thinking right about quantum mechanics. The limit is not what you think it is. And that's a thing I'm going to talk about a little later. And then over here on the right is David Lee, who in the early 70s wrote a interesting PhD thesis where he talked about testing general relativity using gravitational waves. And the idea was it's a good thesis project because it's probably going to happen soon. And then for those of you who know, this is Sander Kovac. He's the first and original Uchibachi of the tape share group. Time moves on and machines start to arrive. This guy is still around. This is Ron Drever, who ran the labs here starting in 1980 and all the way into the 90s and then 2000s. When I got here, he hesitatingly parted with some of his equipment and allowed me to get started. And here's Robbie Vogt, who gives us some interesting pointers now and again, but really got this whole thing going forcibly back in the 80s and 90s. Now onto some modern age. Now we have color photography. And this is just the LIGO group at Caltech, but the people who have been working on the machines and making them actually detect signals are the groups in Washington, which is a large group there, and the group at Louisiana. And all of these, the students, these are not all students, all of the students and postdocs here have had some intensive visits here where they've worked with us in the laboratories before going out to the sites. So we have a strong connection. Well, if there was no noise, we would have had these signals for you long ago, but it's been a long road. As Alan mentioned, the signal doesn't appear in the Virgo detector, although that was important. And our idea was that we would build these two detectors in the US and they would be the same. But you can see that they're not really the same. The signal shows up in Louisiana before Hanford. And the reason for that is we're still not limited today, we're still not limited by the fundamental laws of physics. So Vladimir Brzezinski would not be happy. But we're moving toward happiness, I hope. Here we go. So this is a similar animation to what you've seen. But here we're showing the strain from the gravitational wave. And if you pause and go back, this is this tidal stretching, bulging that Alan mentioned. Let's see if I can do this. So you see it starts off spherical, and then just before the end, it starts going into this teardrop shape. And this is just a simulation, so we're not exactly sure that this is what happened, but we desperately want to know. the nuclear density of these neutron stars is such that it's higher than the usual nuclei of gold and iron and stuff that you have here on Earth. And we really want to know how this behaves and what's making the neutron star so stiff or not so stiff and what's going on inside of it. And so the rest of this is sort of accurate. The rest of this is shaded here because this is speculative. We don't really know what goes on here at the end. And one of the biggest questions we want to answer is, when this happens, does it remain a neutron star or does it collapse into a black hole? And as you can kind of infer from this movie, you can only tell that by looking at these waves right at the end. And the signature of these things will tell us really what's going on. Are we left with a hypermassive neutron star remnant, or does it collapse? So we do have signals from gravitational waves and electromagnetic observatories. And what are we going to do with that signal? Well, I think everyone here knows one of the great things of modern astronomy is you can use it to find out how fast the universe is expanding. And when you see something like lightning, you can ask yourself, how far away was it? Or am I in danger? And the rule of thumb is that if you hear the thunder within 5 seconds of seeing the lightning, you're in trouble. It's close by. And the reason you can do this is because you know there's a relationship between the speed of light and the speed of sound. And similarly, we want to do something like this using the signals we have. This is a timeline of the events. We had the gravitational wave signal a few seconds after the gamma ray burst, and afterwards signals from all of the other bands. And as Greg mentioned, the radio is still coming. And what will we do with this? Well, if you just had the electromagnetic signals, of course, you can do things like find out about the rate of expansion of the universe and the Hubble constant. And we can also do this using gravitational waves. And the way that we do this is quite different. Alan showed you this picture of how the different binary black holes merge and how long it takes them to merge. And how fast they merge and their frequency evolution has to do with the masses. And this signature is so unique that it serves as a standard siren for us. When something like this happens out in the universe, we know not just what its frequency evolution is, but we can also tell exactly how loud it will be. And since our detectors are calibrated, we can just look at that signal and say, this is how far away it was because of its amplitude. And so it gives us a unique measure of the Hubble constant, and we can compare those and find out if things are as we expect or if there's an anomaly. So here I'm showing the two measures of the Hubble constant, one in red from the Planck satellite, and here from supernovae. And this orange curve is our estimate of the Hubble constant. You can see we're sort of reaching across the aisle here. This is a non-controversial measurement so far. We are sort of in agreement with both red and blue sides. And this is what we get from one neutron star, although it was very close. This is just our first one. And as we move on into next year and the year after that, we hope to get dozens and dozens of these so we can narrow down this distribution. We won't be doing this in isolation, so surely these error bars will go down, but hopefully in 2019 you'll see a graph like this, which will have an orange bar, a red bar, and a blue bar. And you know, I hope that they all disagree. That's the best. That's the best. We've been showing you these pictures of noise, which are sort of correct, but this image makes it seem like it's a broadband white sea of noise with a signal on top of it, and I wish that were the case. But in fact, it looks a little bit more like this, and this axis is frequency, and this axis is strain, so this is sort of like the fluctuations of our mirrors or how well we can measure things. And here's a comparison in equivalent units between the three detectors. And the Virgo detector has just turned on, and it's amazing the progress that they've had. They've caught up to us really quickly. And the difference between the two LIGO detectors is this. And you can see, well, you know, it's not the same. They were built to be the same. We're told that they're the same, but they're not the same. And the reason is, Well, I'm not going to go into the reasons. But there are differences, and there are things to be done to improve them. But finally, even the best one we have right now, the one in Louisiana, is limited by the quantum fluctuations of light, just the shot noise in the light, above 100 hertz or so. And these thin traces here that you see correspond to the signal strength of binary neutron star merger in those detectors. So this green line is here, and you can see this is why Virgo didn't see it. It's unfortunately placed in the sky. And the signal is a bit bigger for the 2 LIGO detectors. But here around 500 hertz or a kilohertz, we're running out of signal-to-noise ratio. It's almost invisible. And this is why we can't really resolve what happens at the merger time. So we want to improve these things. So one of the tricks that we have is to use this technique introduced to us by Carl Caves, which is called the squeeze light technique. And the trick to making the squeeze light technique work is, in the interest of time, let me move on. I'll skip that. So there's some trick, which if you ask me, I'll tell you about. But this is where the LIGO detectors are right now. These are 2 simulations of binary neutron star signals that we may have had. We know that this part is correct, and then around here, the picture gets a little fuzzy, and so there's still multiple theories. One of these is probably ruled out at this point. We expect in about a year and a half, we should be at this level of this white curve, which is the ultimate advanced LIGO sensitivity, and maybe a bit beyond. And then finally, it's interesting, Mansi mentioned neodymium. These interferometers right now are powered by neodymium lasers. And the future is a little further on the periodic table. And with the installation of holmium or thulium lasers, we expect to get a big bonus on top of what advanced LIGO can do and resolve these final waves. So it's it's not so easy, but let's see if you can do it. So this is one idea of what a neutron star in spiral sounds like. And so pay attention to the ending there and try to keep it going in your ring buffer. Let me do it one more time. I think everyone should be able to, this frequency is not too high. So you hear the ending. And here's another one. Let me do it another time. So you hear, it's almost the same. Oh. Back up. All right. Sorry, PowerPoint will not let me play that again. Anyway, if I had played it a few more times, you would get it. All of the difference happens right at the end. The first million years and even the last few minutes, which we can detect with the LIGO detectors, is not enough to really distinguish between these different models. But just getting that little bit at the end, which is the difference between a low-frequency bloop and a high-frequency chirp, is enough to distinguish between these models, hopefully. So I think this story is really about people. And the first picture I showed you was from the early 70s. And there's a lot of tenaciousness which went to bring that into the 90s and then into the early 2000s. And our group is just getting bigger and bigger. And one of the secrets of this squeeze light technique, which I would tell you about if I had time, is the fact that we have these new people coming in working on it, and they all have new ideas. So the ideas we had from 10 years ago are pretty much out the window, and because of our summer undergrads, we're really moving in new directions. So what's to be done next? Right now, the LIGO detectors are off, so don't worry, there will be no more text messages in the early morning. You can go back to Ireland if you like. Probably at the end of the summer, sometime in the fall, if things go right, we'll turn back on with root 2 to 2 better sensitivity and most of this low frequency noise magically removed. And you should expect hopefully 10 times more signals at that point. Really, the way this is working for us is we have three things coming together in some sort of coherent way at the end, which is we have the power of theoretical astrophysics and numerical relativity in this building. And then we have the precision measurement investment, which has been going on in condensed matter and AMO and within the LIGO group for now for almost 40 years. And couple that with our new insights into how quantum measurement can work as part of the IQIM here. These three things are kind of adding up together in ways that definitely I wouldn't have expected when I came here about a decade ago. But it's really promising for the future. I think we expected we might make sort of incremental improvements, but I think, as I've shown you from some of those previous graphs, within a decade, the kind of reach we should have for binary neutron stars should enable us to make weekly detections at least, if not more. So we have this new era of astronomy. We have these new tools which will tell us about cosmology. And so far we've had binary neutron stars, but and it's great that the signal was so loud, but I think sometime next year you should expect that we're going to find something new, which doesn't even have a name yet. And then for that, you'll all be getting text messages early in the morning. Thanks.
Okay, so we have time for some questions. Anybody wants to ask about squeezed light or anything else? We'll take maybe, let's see, where are we? Maybe 10 minutes for questions and discussion. So if you have a question, raise your hand and direct it to one of the presenters.
So is this 1.7-second delay something predicted by any of the theories between the gravity wave and the gamma meters?
So I can take that one. So the question is, after the gravitational wave merger, there was a 1.7-second delay before the gamma ray signal was detected by the Fermi satellite. And is that something that was expected or surprising? I think it was a bit of a surprise. I mean, people have predicted different lengths of delays from milliseconds to seconds. And in the cocoon model that I presented, it actually is very helpful because you need the two neutron stars to merge, you need a jet to be launched, you need the jet to form a cocoon, and then the cocoon to break out. So a couple of seconds is perfect to see the wimpy gamma rays that we do end up seeing after the couple of seconds delay. But it's a very, very important clue.
Back there.
Okay, so I guess the question for Alan. So Monty and Greg nicely explained why the viewing angle matters so much for the electromagnetic part. How do the waveforms change the gravitational waves based on the viewing angle?
Okay, so the question is about not so much the gamma rays, which are beamed, but what's the shape, if you like, or distribution of gravitational wave emission. And there, gravitational waves are very different. Electromagnetic waves can be very strongly beamed. Radio can be very strongly beamed. Gravitational waves, much harder to get them to be very strongly beamed. And it goes along with the fact that the sources of electromagnetic radiation are the incoherent motion of extremely energetic particles, electrons. And in the case of gravitational waves, it's through the coherent motion of very large objects like neutron stars or black holes. And that makes the angular distribution or the beaming pattern of these sources much, much broader. And that's why we can detect gravitational waves even if from a merging system like this, even if the gamma rays are beamed in a completely different direction. And that's why I was expecting that the very first binary neutron star systems that we would observe would not be accompanied by gamma rays. They'd probably be beamed in some other direction. The beaming angle might be as small as 5 or 10 degrees. They'd go somewhere else. We wouldn't detect them. We'd only detect the gravitational waves, which are much weaker beamed. Boy, I was wrong for this one. Polarization. And again, the electromagnetic radiation is polarized transverse to the direction of motion. Electric fields and magnetic fields are vibrating perpendicular to the direction of motion of the electromagnetic waves, and it's a pattern known as vector or dipole radiation. And for gravitational waves, the prediction from Einstein is that it's not a vector but a tensor polarization. It's not dipole, but it's quadrupolar. And that produces a different pattern of the strength of the signal at the Hanford detector, the Livingston detector, and the Virgo detector. And the pattern that we observed was in perfect consistency with the tensor polarization, and not at all consistent with the vector or scalar polarization. It's the first time that we've observed the polarization of gravitational waves, and it required 3 detectors, and it once again confirmed that, yeah, looks like Einstein's right again.
So in your cocoon model, I was wondering how much mass you need around the jet launching object to actually train the jet, and how much of that would be ejected a few seconds before merger?
That's a great question, Vikram. So let me repeat that. The question is how much material was ejected before the merger, and that led to the formation of the cocoon. And we estimate something like 0.05 solar masses of ejector was ejected both during merger and then just after the merger. And that's enough, that's a lower limit, and that's enough to form a pressurized cocoon that would eventually break out. You could have more, you could have less. That mostly affects how, whether or not the jet would get choked or suffocated, and the radio will tell the answer on that one.
How energetic was this event compared to black hole or supernova?
How what were they? Energetic. In gravitational waves, much less energetic, and in particular, so the question is how energetic was this compared to binary black holes? So for binary black holes, we have signals with signal-to-noise ratio on the order of 10 to 20 from sources that are a billion light years away, or several billion light years away. For this event, which was 100 million light years away, the signal-to-noise ratio was not 10 times bigger, but only about twice as big. So in gravitational waves, it was much less energetic, and probably instead of 2 or 3 solar masses worth of energy converted to gravitational waves, this is more like 5% of a solar mass, much wimpier in gravitational waves. In every other form of radiation,
That's a lot, right? Because that would be, I guess, a billion times the luminosity of the Milky Way, roughly.
So when the 2 neutron stars are very close to each other, so by looking at the gravitational principle, can you say something about how the magnetospace interact? Because they might have an energy contribution.
I couldn't make it out, sorry.
So the 2 neutron stars have strong magnetic fields, let's assume, and when they get close to each other, the magnetospace will interact. So can we learn about that by looking at gravity?
I can try that one. So the magnetic torquing could be sufficient. So the question is about whether the magnetic fields in the neutron stars could change the signal. And of course, they will make a very big difference in the ejecta. But for the gravitational waves, they can, in principle, cause what's called magnetic torquing, where it's, the angular momentum is changing therefore the speed at which the gravitational waves orbit each other, and that would be imprinted in the waveform. It's a subtle effect. It happens at the highest frequencies where, as I mentioned, our signal starts getting buried in noise. So far we don't have any indication, any ability to make statements about the strength of the magnetic fields that may be involved and the effect they may have had on the gravitational waves. For that, we need a much more sensitive detector. Rana is going to deliver.
So we'll take one more question because Channel 7 is here and the panelists need to go out and be interviewed. But everybody else is welcome to go out to the patio and talk. We'll take one last question in the back there.
I have a question about the cocoon model. Have we seen evidence of the cocoon model in other transient events?
I think this is the first indication of an event that's close enough to investigate the cocoon model. So it's been theorized previously, but there's never been an observation of an event close enough to investigate directly whether or not a cocoon has occurred. So we associate neutron star mergers potentially with short gamma ray bursts. They're at very great distances, typically halfway across the universe. This is in our own neighborhood by those standards. So this is the first time we can actually investigate things like, does it have, do you have a radio emission signature like a cocoon? Is the X-ray emission like a cocoon? So this is our first chance to investigate that.
Okay, so please join us on the patio panel. I think Debbie here will tell you where to go.